Good evening to all. So in the last lecture, we have discussed about the passive transducers or active transducers. So in the passive transducers are classified based upon the electrical elements, that is passive elements such as resistor, capacitor, inductor, and also active elements. So we are discussing about the passive transducers using resistive elements. By considering the resistive property, the passive transducers are developed. Okay. So under such passive transducers, we are discussing about strain gauges. We are discussing about the strain gauges. So the first one we are saying about the potentiometers, linear and angular potentiometers. Okay, and also photoemissive cells, photodiodes, and coming to the strain gauge. So strain gauge is also used to measure the strain which is applied on the this strain gauge. Okay, so it will be works on the principle of whenever there is a change of the length or cross-sectional area changes, its resistance will be changes. By the application of the strain, there is a increase or decrease of the length of the conductor will be takes place. When the length of the conductor will be changes, its resistance will be changes. So based upon this basic principle, we can find out the variation of the or change of the resistance, and that change of resistance corresponds to the change in the dimensions of the conductor. The change in the dimensions of the conductor is corresponds to by applying the amount of the strain. Okay, so that variation of the resistance or a change of the length will be identified by a gauge factor. The gauge factor gives the how much variation is occurred. For that amount of change of the length, how much change of the resistance also happens in a given conductor. So that will be found out by gauge factor. It is a change of the resistance delta R by R to the change in the length delta L by L. So for the semiconductors, its value is very high, 120, whereas for metals it is around 2. And the strain gauges are basically classified as two types. One is metal strain gauges and semiconductor strain gauges. Metal strain gauges and semiconductor strain gauges. Metal strain gauges are again classified into two types: unbonded strain gauge and bonded strain gauge. Unbonded strain gauge and bonded strain gauge. So the figure below shows the unbonded strain gauge. The structure of the configuration of the unbonded strain gauge. So here we will consider two members. So this one is the stationary frame or stationary member. We can call it as a stationary member. And over that we have another member that is called as armature, and this armature is above this stationary member, and we will use a resistance wire. Okay, so this resistance wire is wound around some fixed slots. So one slot is fixed on the stationary member. Okay, if we consider the resistance R, one pole, we can say it is a slot or pole. Okay, so one pole is placed on the stationary member. This one is entire one is the stationary member, and another pole is placed on the moving member. So this one is the moving member. Okay, so whereas R2, we will place one side resistance wire is wound along these poles. Okay, so one pole is at the stationary member and another pole is at the moving member. So like this we can use the four resistive wires. which are wound over this insulating poles. So these are considered as insulating poles. Okay. So suppose we apply some pressure or strain or some displacement over the station moving member. Okay. Suppose we apply some displacement, okay, displacement over the moving member. Then what happens? This moving member will move towards the right side. Moving member moves towards the right side. Then the resistance R2 and R3, the wires of resistance R2 and R3 will be stretches. Resistance R2 and R3 are stretched, whereas the stress of the resistance R1 and R4 is decreases. You can understand. So this one is the movable member. Okay, this one is the movable member, and this movable member is placed above the stationary member, and we will wound the wire on these insulating poles. Okay, so it is like one pole on the stationary member and another pole on the movable member. Like that, we can place these wires. When the movable member or armature is moves in one direction, or suppose consider the movable member is moved to the right side, then these R2 and R3 resistance wires will be stretched, because here this is fixed at the stationary member. Okay, due to movement of this movable member, another pole is on the movable member. That's why when this movable member is moves to right side, the attached wire to the this insulated pole will be also moves, or the length of this wire will be increases, or the wire will be stretched. And coming to R1 and R4, these two resistors, its stress will be decreases, because previously it is in a stress mode. Stress mode. Okay, because these two are connected as a stretcher mode. Okay, now movement of this moving member, this wire will be compresses. You can say compresses, or releases its strain, or stress is decreases. So like this, R2 and R3 resistance wires will be stretched. When the stretched, the resistance of these wires will be increases. When the stress will be releases, it means it compresses, the resistance of these wires will be decreases. So it depends upon the type of length increasing and decreasing. So previously we have seen, so when the length of the conducting wire will be increases, its resistance will be also increases based upon the R is equals to rho L by A. If the length is increases, resistance of the wire will be increases. If the length will be decreases, its resistance will be decreases. So based upon this, when there is a stretching, and it means the length will be increases, and due to that the resistance of this R2 will be increases, and similarly R3 also increases. And for R1 and R4, the resistance will be decreased, because this length will be decreased. Okay, so the variation of this particular change of resistance will be identified by using a bridge circuit. So this is the Wheatstone bridge. So Wheatstone bridge, I think you may know this. So Wheatstone bridge is used for measurement of the variation of the resistance. So here this is the arm 1. Generally, this bridge is called as this is Wheatstone bridge. In Wheatstone bridge, this is the arm 1, ARM, arm 1. This is the arm 2, arm 3, and arm 4. Okay. So in these 4 arms, we will connect these resistors. Okay. We will place this resistance R1, R2, and R3, R4. If there is any variations by the application of the strain or stress, okay, so due to that application of this strain or stress, there is a change in the resistance. The change in resistance will be identified by applying some external voltage to this bridge, and that variation of the resistance will be reflected on the deflecting meter. This deflecting meter will be shows the how much variation of the resistance is occurred. So at that corresponding current will be flowing through this meter. So that meter will be moves this deflection pointer. That point will be gives the value of the change in current. Okay. So that this meter will be calibrated in terms of the strain. This meter will be calibrated in terms of the strain. So like this, we can use the unbonded strain gauge for measurement of the strain. Okay. So here we are using all these strain gauge, all the resistance wires, the same Wheatstone bridge. Okay. So there is no need of compensation of the there is no need of temperature compensation in this unbonded strain gauge. So the next one is bonded strain gauge. The next one is bonded strain gauge. So in the bonded strain gauge, we will use a wire which is like a wound zigzag fashion, and this lead wire, this is the strain gauge. Okay, so this strain gauge is cemented between the two paper covers. Okay, so this is the one cover, top cover, and this is the bottom cover. And this cover is corresponds to a thin paper over this strain gauge. This is the strain gauge. Okay, this strain gauge is covered by two covers, paper covers. Okay, so after this particular arrangement is connected to the structure. Suppose we can use for measurement of the weight of some material. Okay, for that particular structure will be attached below that particular structure. Okay, suppose if you go to the market, so you can observe a platform is there. Okay, and for that platform below we will place this particular strain gauge. I mean, this strain gauge is attached at this surface of the platform, and we will place the material on this particular platform only. Okay, when the weight is placing on this particular platform, the weight will be transferred to the surface of the platform, and below that we have a strain gauge. So that effect of the strain will be applied on the this wire or strain gauge. Okay, due to that the resistance increases or decreases, and due to that the variation of the resistance will be identified by using the Wheatstone bridge. So like this we can use the bonded strain gauge. So whereas this bonded strain gauge, we will fix this strain gauge to the surface of the structure. So where we have to measure where we place the weights. Okay, so we have to bond, we have to make a cement with that structure. So that's why this bonded strain gauge is mainly used for the strain of the structural surface structure, strain which is occurs at the surface of the structure. Okay, so after that the second one is the semiconductor strain gauge. So whereas in the semiconductor strain gauge, in place of this coil, conductor coil, we will use a slices of the silicon. The silicon material will be placed as a slice of the silicon will be placed in the place of the conductive wire, which is seen in the bonded strain gauge. In place of this conductive wire, we will use a slice of the silicon material. So then this particular silicon slice will be attached to the structure of the structure where we have to measure the strain. Okay, so by connecting this semiconductor material as a converting element, so it is having a gauge factor of around 120. So it is offering very high value of the gauge factor. when compared to metal strain gauge, bonded or unbonded strain gauge, when we use the silicon material, okay, silicon replaces the wire of or foil pattern as a conductor. So it will act as a conductor. Okay, the same as we have seen in the bonded strain gauge, we will replace that coil or conductor with the silicon material, slice of the silicon material. So when the strain is applied on this structure, so that strain will be connects to the or applies to the silicon material. So due to that, the conductance of the silicon material will be changes. So it will offer very high value of the gauge factor. So 120. So by varying the amount of the impurities in the silicon, its conductivity can be controlled. How we can get this particular type of the value of gauge factor means, so we can add some impurities. So all of you know that in PN junction diode, so we will add some impurities to the pure semiconductors. By that, the conductivity of the material will be changes. Okay. So based upon that, the conductivity of the silicon material will be changes and corresponding conductance will be identified. So here one more thing we can observe that. So if suppose we are using a strain gauge, it is nothing but a conductor. So conductors are the resistance of the conductance will be changes with the change of the temperature. So they are dependent upon the temperature variation. Okay. Similarly, semiconductors also, its resistance will be changes on the depend upon the temperature. The temperature is increases, the resistance of the semiconductor materials and conducting materials or metals will be changes. Okay, that's why we have to provide some temperature compensation devices. We have to provide some temperature compensation. So if we consider for the strain gauges, we can use minimum 2 strain gauges for measurement of the weight. One strain gauge is used for the measurement of the strain, and another strain gauge is just placed near this strain gauge. Okay, and this strain gauge does not provide any output due to the applying strain. The second strain gauge does not provide any output due to the applied strain gauge, because we are not applying any strain to the second strain gauge. If there is any temperature changes from room temperature to some 27 degrees Celsius to some other 40 degrees Celsius in summer, the temperature is increases around nearly 15 to 15 degrees Celsius, above 15 degrees Celsius. For such variation of the temperature variations, this particular semiconductor materials or the metals, their properties will be changes, its resistance will be changes. To compensate that amount of the temperature variations, we will also connect another strain gauge near to the measuring strain gauge. Okay, so if any temperatural changes, that temperature effect will be applied on the measuring strain gauge and another with the compensation strain gauge. Both the strain gauges will be changes its resistance equally. Okay, so we will connect these two in opposite side. So if there is any effect on the measuring strain gauge, that will be compensated by the second strain gauge. Okay, so like this we can use the minimum 2 strain gauges. So this will be used as these strain gauges will be connected as Wheatstone bridge. So what we have seen in the previous Wheatstone bridge, one measuring device is connected at so this one is arm 1, this is arm 4, arm 2, this is So here we will connect a detector or ammeter. Okay. So generally this is the arm 4, this is the R4. So here we will connect the measuring strain gauge. So in opposite to this one, another this is the R3. So R3 is the second strain gauge. Okay. So this is the R1 and R2. If there is any variation of the temperature, so both the resistances of the strain gauge will be changes. Okay, and the finally R4 gives the only the value of the strain related resistance value. So like this, we will connect the two strain gauges in the same bridge. We will provide the compensated output value. Okay. If there is any doubts in this regard, you can ask. So how many are it? 14. So up to now we have discussed about the passive transducers using resistive elements. So now we'll see about the passive transducers using inductive elements. So by using the inductive transducers, we can identify the variation of the displacement. So these inductive transducers are especially used for the measurement of the displacement. Okay. So how we can see? Suppose we can consider a permanent magnet core. So this is the core, which is a magnet, permanent magnet, and over that permanent magnet we are wound a wire. Okay. This will form as an inductor. This will form as an inductor. So for this particular type of the inductor, so how we can change the inductance? So from the basic formula, all of you know this, L is equals to mu naught into mu r into A into N square by L. So where capital L is the inductance of the coil. Okay, and mu naught mu r is the absolute permeability and relative permeability, and A is the cross sectional area of the coil, and N is the number of turns of the coil, and the small l is length of the coil. Okay, so to change the inductance of this coil, so what parameters are required to change? If we consider the length of the coil does not change. If you change the length, the inductance value will be changes. But for a given wire, the length of the coil is constant, so it is not affected. Okay. If you consider the N is the number of turns of the coil. So if the number of turns of the coil is also constant, and the another one is, this is the cross sectional area. So A is the area encircled by this coil. Okay, it is also constant, and only one thing we can consider, there is a change of the permeability. There is a change of the permeability. So the permeability that corresponds to the flux which is flowing through this core, and also the flux which is flowing in the air. So okay, you suppose this particular magnet is moving from left to right, that is by applying some displacement, the core will be changes its position in the coil. Then this is a magnetic core. Okay, when the magnetic field will cuts this particular coil, the EMF will be generated in the coil. Okay, so here the magnet, permanent magnet is moving, and whereas coil is constant. The coil is constant. So due to that, the magnetic field will cuts this coil, and EMF will be generated in this sum. So the movement of the core depends upon the applied displacement. If the displacement applied in the forward direction, this core will be also moved to the forward direction. Due to that, the flux linkages with the coil will be changes. Due to that, EMF will be induces. That EMF corresponds to applied displacement. So like this, we can find out the inductive transducers based upon the permanent magnet. Okay, and when suppose we can use an electromagnet, a, a ferromagnet material is used as a core. So in such situation also the inductance of this coil will be changes. So that inductance depends upon the permeability of the core. Okay, if the core will be changes, the permeability will be changes. Okay, based upon that, the inductance value will be changed. That inductance value will be measured by using AC bridges. So we have DC bridges and AC bridges. Previously, we have seen that Wheatstone bridge is a DC bridge. So the value of the change of inductance will be measured by AC bridges. So we have some AC bridges also there for measuring of the variation of inductance and the variation of the capacitance. So this is another type of capacitor transducer, that is a variable reluctance transducer. So reluctance is the opposite to the permeability. Opposite to the permeability. So in this case, the core remains stationary. In the variable reluctance transducer, core remains stationary, but the air gap in the magnetic path of the core is varied. So the air gap of the core is changes. So due to that, the reluctance of the transducer will be changes. Okay, change of the effective permeability. So that will be identified by using the change of the inductance value. So that inductance value is measured by using AC meters, AC bridges. And the another one is linear variable displacement transducer. This is not transducer. It is a linear variable displacement transformer. Here we have a term, that is transformer. Okay. It is LVDT corresponds to linear variable differential. Oh, they are given wrong here. So LVDT is nothing but linear variable differential transformer. Okay. So linear variable differential transformer. Okay. So it is it's like a transformer. So basically it is a transformer. Basically it is a transformer. So here we are shown the construction details of the LVDT. So LVDT is linear variable differential transformer transducer. LVDT transducer. So it is mainly used for measurement of the displacement. So whereas in previous case, this variable reluctance transducer and inductive transducers, for the displacement is very, very small, and there is some non-linearity will be present in the inductor coil. So those non-linearities will be cancelled by using the LVDT. By using the LVDT, the non-linearities which are caused in the inductive coils will be cancelled by using this LVDT. So if you observe this figure, so in a transformer, it's like a transformer. So for the transformer, we have two windings. One is primary winding and another is the secondary winding. Whereas for LVDT, so we have two secondary windings. Two secondary windings. In between, we have a core. Primary winding, core, and two secondary windings. This is the secondary winding 1. This is secondary winding 2. So we will apply the input at the primary side, and this core will be placed at different positions, and the secondary windings 1 and 2 are connected in series opposing. Series opposing. It means the generated voltage will be differentiated. Okay, subtracted. The difference of output voltage is difference voltage V1 minus V2. So depending upon the core position, the voltage V1 and V2 will be generated in the secondary windings. Isn't that initially the core is at center to the both the secondary windings. Okay, so suppose this is the center position which is equal distance between the two secondary windings, and due to that the flux linkages from this primary winding is equally distributed to the two secondary windings, and due to that the EMF will be generated in the two secondary windings V1 and V2 are equal. That's why V1 minus V2 is equals to 0. I think you are getting this concept. Okay, suppose the core is moving upward direction, then what happens? The most of the core is connected with the secondary winding 1. It is less connected to the secondary winding 2. That's why the flux which is linkages with the core to the two secondary windings, the first secondary winding has more flux linkages, and due to that V1 is V1 is more than the V2, and the difference value is V1 minus V2. Okay, suppose we are moving further, the core is moving further in the upward direction. The core is moving further upward direction. Then what happens? The core completely covers this secondary winding. It does not covers the secondary winding 2. Okay, and due to that, the most of the voltage will be generated in the V1. So V2 is, in such case, V2 is 0. Then most output voltage V0 is equals to V1. Okay, so that is the extreme position. Suppose from the center position to the core is moving to downward direction, then some part of the core is connected to secondary winding 1, and another some part of the core is connected to secondary winding 2. Okay, so due to that the flux linkages more with the secondary winding 2 and less linkages with the secondary winding 1, and due to that the voltage is V0 is equals to V1 minus V2. So in this case we will get the minus V0. That is V0 is equals to minus V2. Okay, so suppose further we are moving the core to the downside. Now in this case the core will be moved totally out of this secondary winding 1. So it will fully covers the secondary winding 2. In such situation the primary coil will be links with the secondary winding, flux linkages with the primary winding, and secondary winding 2 will be more, and due to that the most of the voltage will be generated in the V2. Okay, the voltages which are produced in the V1 and V2 are corresponds to the position of the core. So here in this case we at the extreme downward position we will get the V0 is equals to minus V2. V0 is equals to minus V2. Okay, so like this we can have the output voltage which are corresponds to the core position. So the core will be moved up and down depending upon the applied displacement. So here you can identify when the core is moving to the downward direction, we can get the negative sign. This negative sign will indicates the direction of the displacement, the direction of the applied displacement. If the core is moving to the upward direction, it is positive. When the core is moving to the downward direction, it gives the negative sign, but magnitude is the positive only. So sign indicates the direction of the applied displacement. So that is the one thing. So this will be represented by, so this is the forward direction. You can consider this the displacement in terms of the 1. 2, 3 like that. We can have 5 also. On the left side we have -1. It means negative direction. 1, -2 like this. Up to -5. So minus indicates the opposite direction. Okay. So here this is 2, 3, 4, 5. Okay. So if the displacement is at 1 centimeters, you will get this much of voltage. This one. Okay. So similarly at 2 centimeters, we will get another difference of voltage. This is the voltage line. Y-axis is voltage line. At this point. Similarly, up to 5 centimeters of displacement, we have a graph like this one. Similarly, when the core is moving in opposite direction, so we will get the positive value, but that indicates the direction. So it is also in the negative direction, like this. Like this, we can get the LVDT characteristics. So up to certain amount of displacement, it offers the linearity. It offers the linearity. After that, it is providing the non-linear characteristics. So that's why this one is called as, up to this point, it is offers the linear characteristics. So that's why this is called as linear variable differential transformer. Because up to this point, the non-linearities are compensated. Okay, so that's why it is linear transducer, and it comes under category of the passive transducer. So here we will apply the carrier signal. So at the primary side we will apply the carrier signal. Okay, so when we apply the carrier signal to the primary side, so we will get the output. It is a modulated signal. From that modulated signal, we have to separate the actual measuring signal. Okay, so the session is closing within 1 minute. So we will continue in the next session.